Hey everybody, what we're going to be discussing in today's lesson is something about functions known as a one-to-one function and how to create and prove whether functions are inverses of each other or not. Now let's talk about what one-to-one functions are. A one-to-one function goes along with the idea of what your Algebra 1 teachers originally told you about how to tell if something is a function or not. Going back to Algebra 1, one of the things that your algebra teachers should have told you about was in order to prove a relation is actually a function, is that none of the x values can repeat. And there's a variety of things that they showed you as far as, well, we could show with a graph, with a mapping diagram, with ordered pairs, several different ways to show that none of the x numbers repeated. And one of the primary things that they probably talked to you about is something known as a vertical line test. And that was one of the ways that you were taught, how most algebra students are taught, that that a relation is a function. To show that none of the extra values repeat, does the function pass a vertical line test? Now, one of the things that we're going to be discussing here is something known as a one-to-one function. So it's not so much are we trying to see if something is a function, we're trying to see if something is a one-to-one function. Now, again, something that makes a function says that the x numbers can't repeat. So something that makes a one-to-one function says not only can the x numbers not repeat, but the y numbers cannot repeat either. Okay, so let's take a look about a couple of things that we can do. Not only can we look to see if something is an ordered pair or not, but from a graph, we can check to see is it a one-to-one function by checking to see not only does it pass a vertical line test, but does it also pass a horizontal line test. So for instance, here, if let's just take the parent function of a line, y is equal to x. If we were to graph that and then draw, some vertical lines to see does it pass the vertical line test, we'd say, yeah, it works. And at the same time, we could pick vertical lines or horizontal lines and say, okay, well, if I draw horizontal lines, do the horizontal lines touch the graph at only one place each and every time? And in this case, yes, they do. So we would say that this is a one-to-one function. It almost looks like an absolute value thing. So let me, one-to-one, there we go. Excuse me. So let's take a look at another function. F of x is equal to x squared, the quadratic parent function. Quadratic parent function goes something like that. And again, if you take some vertical lines, you'll see that, well, it only touches the graph at any one point. But if we were to try and check with the horizontal line test, we can see if we take a horizontal line that the y numbers repeat. Because the y numbers repeat, we would say this is not one-to-one. And that is what the horizontal line test would allow us to do, is not just see if something is a function, but to see if something is a one-to-one function by checking if the y values repeat. And here's another method. If I happen to have a set of ordered pairs, we want to know, is it a one-to-one function? So I'm not asking you to check if it is a function, I'm letting you know it is a function. But is it one-to-one? So look at the y numbers. Here, the y numbers repeat. So it is a function, but because the y numbers repeat, it's not one-to-one. So it's not one-to-one because the y numbers repeat. And in the second example, positive 5, negative 3, positive 4, negative 2, none of the y numbers repeat. So here we'd say, yes, it's one-to-one because the y's don't repeat. Okay, so that is, what a one-to-one function is. It is a function, but not only do the x numbers not repeat, but the y numbers don't repeat also. Now what we're going to be doing is talking about inverse functions. Now inverse functions are actually really kind of important to have some background information on, because what we're getting ready to move on to in our college algebra curriculum is functions that are inverses of each other. True inverses. What we're eventually going to be getting into are exponential functions and logarithmic functions, and those are inverses of each other. So knowing a little bit about inverse functions is important going into studying exponential and logarithmic functions. Now we're going to be doing two things with inverses to start with. First, we're going to be saying, how do we develop an inverse function? How do we show that something is an inverse of something else? And secondly, once I know that this function and this function are supposed to be inverses of each other, is there a way that I can check to see that they are actually inverses? So here, the steps that we have, whatever function I am given, I'm going to take f of x or g of x or h of x, whatever notation I'm working with, and I'm going to just go back to using x's and y's. So if I have f of x, I'll just put y there instead of f of x. Then what you do is you swap the x and y in the problem, and then solve the new equation in terms of y. Once I've solved for y, I replace y with my inverse notation, which is f of -1 with x. So let's take a look at this example. Here we have a linear function. F of x is equal to 2x plus 3. No big deal. Linear function, we could graph it, we could do all kinds of stuff with it. But what I want to know is, what is its inverse? What is the inverse of this? So what we're going to do is we're not going to write f of x, we're going to just write y. And that's it. Once I've substituted the function notation with just y, the next thing it says to do is to swap the location of x and y in the problem. So y is equal to 2x plus 3 becomes x is equal to 2y plus 3. And from here, what we do is solve the equation for y, get y by itself. So move the 3 over from the right side to the left side. I'm going to get x minus 3 is equal to 2y. And then divide everything by 2, which would give me x minus 3 over 2 to be equal to y. Now I'm going to change it up just a little bit, and I think it'll be easier to show half x minus 3 over 2 is equal to y. So my final inverse function with the notation would be 1/2 x minus 3 over 2. So here is my inverse function. I really could have done it here too, but for the purposes of things that we're going to be doing with the function later on, I think it'll be easier to leave the denominator under each individual term. So there is the inverse of this function. Now I'm going to show you something here. Those of you that are going to be in class, I'm going to try and have you do something with a graphing calculator to show you some of the properties about inverse functions. So real quick, I'm going to just try and sketch this one, so at the very least, anybody watching the video can have an idea what we're talking about if you don't have a graphing calculator. I'm going to go ahead and graph both of these functions. 2x plus 3 says my y-intercept is at 3, and I have a slope of positive 2, so up 2 and over 1, or down 2 and over 1, and I should have a line kind of like that. And I'm just freehanding it, so bear with me. And so let's graph our inverse function. Now the inverse function has a y-intercept of -1.5. So -1, -2, so my y-intercept is about right there. And I have a slope of a positive 1, so up, or a positive 1/2, so up 1 and over 2, or down 1 and over 2. So we're going to, again, kind of have something that goes like that. And if they continue, you'll see that they'll cross. Now, what I want to include here is the linear parent function. Y is equal to x, or f of x is equal to x. If I were to graph that, it is going to go just like this. And I am freehanding it, so it's not perfect, but any functions that are inverses of each other will have a linear parent function, will have a straight line going through the origin as a line of reflection. Imagine if I were having this on a piece of paper and I folded it along the black line that I just graphed. The blue line and the red line would lay right on top of each other. And that is a property of all inverted functions, or functions that are inverses of each other. So those of you that are going to be practicing this in class with me, I'll probably have the graphing calculators out for the purposes of you being able to see that. And because it is a relatively significant thing in terms of properties of inverse functions. So here, again, it's just a little bit more practice. Let's find the inverse function of the one that we have now. We have a cubed function. So this is going to say when I do the inverse of it, I'm probably going to wind up with a cube root function. So let's go ahead and do our properties here. Take the function notation out and just put y. So I'm going to get x cubed minus 5 is equal to y. And swap x and y in the problem. So now I get y is equal to, or I'm sorry, x is equal to y cubed minus 5, and solve for y. So move the 5 over through addition, and I get x plus 5 is equal to y cubed. And at this point, we will take the cubed root of both sides. So the cubed root of something cubed is just whatever the radicand is. So in this case, y. And so I'm going to get y is equal to the cubed root of x plus 5. And so putting our function notation in for our inverse, I would say the inverse is the cubed root. Let me clean that up just a tad. The cubed root of x plus 5. So algebraically speaking, not too difficult. And our last example of how do we show if a function, or how do we get a inverse, same thing, put in y. So y is equal to, in parentheses, x minus 4 cubed over 27. Replace the x's and y's, swap them out. So I'm going to have y minus 4 cubed over 27. And again, because I have something cubed, I should wind up with something as a cube root for my inverse. Get rid of the 27 out of the denominator by multiplying both sides by 27. So on the right side, 27 over 27 simplify to be 1. And on the left side, I'll have 27x equals, in parentheses, y minus 4 cubed. So at this point, again, I have something cubed that I need to undo. So the way I undo a cube is by taking the cube root of something. So anything I do the one side, I have to do the other side. So on the left side, the cube root of 27 is actually 3. But the cube root of x, I don't know what x is, so it has to stay a cubed root. And here, the cubed root of something cubed is just, in this case, the radicand y minus 4. So excuse me. So now I'll move the 4 over through addition, and I will get 3 times the cubed root of x plus 4 to be equal to y. So with our final function notation, I will say the inverse of x, or the f inverse of x, is equal to 3 times the cubed root of x plus 4. And algebraically, it will work that way pretty much all the time. The inverse of a linear function should be a linear function. The inverse of a quadratic function should be a cubic or a square root function. The inverse of a cubed function should be a cube root function, and so on. So the last thing that we're really going to be talking about is how do I check, how do I know the function that I created is actually an inverse of something else? Well, what we're going to do is we're going to take the function that we started with and the inverse that we came up with. What we're going to do is we're going to do something called a composition. Basically, we're going to take one function and put it in to the other function. We're going to substitute it anywhere I have an x. And then we're going to evaluate it. And when I'm done, it should always simplify to just be x. And a second ago when I tried graphing it by hand, I had the y is equal to x thing where I tried to show you that the linear parent function would be a line of reflection for the inverse for the two functions. Well, algebraically, that's kind of why it works out that way. So let's take a look. Here, the 2x plus 3 is a function that we started with, and the 1/2 x minus 3 over 2 is the function that we came up as the inverse. If I take either of those functions and I substitute it into the other function for x, when I evaluate it, it should simplify to just be an x. So let me show you what I mean. I'm going to take the inverse function and I'm going to put it in to the original function, anywhere I have an x. So 2x plus 3 becomes 2 times 1/2 x minus 3 over 2 plus 3. All we're doing is substituting one function into the other function anywhere I have an x. And let's evaluate it, see what we get. So if I take the 2 and I distribute it into the parentheses, 2 times 1/2 is just x, and 2 times negative 3 over 2 is negative 3. And then, of course, I bring down the plus 3. And you can see those are opposites and cancel out. So I'm left with just x. So that worked. But in order to show that it is truly an inverse, I have to do it both times. I have to do it both ways. So now I'm going to take the original function and I'm going to place it inside of the inverse that we came up with. So anywhere I have an x on the function on the right, I'm going to substitute the function on the left. So I'm going to say 1 over 2, and I'm going to substitute the 2x plus 3 in for x, and then minus 3 over 2. And I'll do the same thing. I'll distribute the 1/2 into the parentheses. Well, 1/2 times 2 is just 1, so I have 1x. The 1/2 times 3 is going to give me a positive 3 over 2. And then, of course, I'm going to subtract 3 over 2. And you'll see, again, those are opposites and cancel out. And it just leaves me x. So when I take either of the functions and I substitute it into the other one, they both simplify to be x. So that is the telltale saying that they are actually inverses of each other. So let's try the other example. Same idea. Take the function that we figured out and substitute it into the function that was given to us. So I'm going to say, I'm going to take the original function, and now I'm going to put the function that I called the inverse inside of it. So anywhere I have an x, I'm going to put in the new function. So here, if I substitute the function on the right into the function on the left, I'm going to wind up with the cubed root of x plus 5 cubed minus 5. And as we've discussed, anything that is cubed, or let's see, anytime the index power and the exponent power are the same, they kind of undo each other. So the cube root of anything cubed cancels each other out, and I'll be left with just x plus 5 minus 5, which are opposites, cancel out, and leave me just x. So let's try it the other way around. Let's take the function on the left and substitute it into the function on the right. So I will have the inverse where I substitute the original function. And I'm going to say the cubed root, and here I'm going to get x cubed minus 5, and then plus the 5 from the function that we had. And inside, or underneath the radicand, or underneath the radical, you'll see that the 5s are opposites and cancel each other out. So I have the cubed root of x cubed, and the cubed root of something cubed cancels each other out, which leaves me just x. So there we go. There's the proof showing that the function that we came up with is indeed the inverse of the other function. So last one, and again, it should work out okay. So let's check just to make sure. So I'm going to say f of the inverse. So the function on the right, I'm going to take it and stick it into the function on, I'm going to substitute it into the function on the left. So I'm going to say the 3 times the cubed root of x plus 4, and then the minus 4 cubed over 27. Pardon me. So order of operations, PEMDAS, says do everything inside the parentheses that you can before worrying about the exponent. So you'll see the positive 4 and the negative 4, those are going to combine and cancel out. So now I'm left with 3 times the cubed root of x cubed over 27. So now I will take the stuff remaining in the numerator and I'll raise it to the third power. So 3 cubed is 27, and the cubed root of x cubed is just x. And I have that over 27. And of course, now you see the 27 over 27 simplifies to be 1, which leaves me with just x. Pardon me, I'm sorry, I have something in my throat today. So now, double check, take the function on the left and substitute it into the function on the right. And so the way that we write that is like so. So 3 times the cubed root of x minus 4 cubed over 27 plus 4. All right, and now here we don't have anything inside of parentheses that we can combine, so let's go ahead and start taking the cubed root of things. Well, the cubed root and the cube cancel each other out, so I'll be left with 3 times just x minus 4. And the cubed root of 27 is just 3, and then the plus 4 at the end. So here, the 3 over 3 simplified to be 1, which leaves me x minus 4 plus 4. And of course, those are opposites, cancel out, and leaves me with just x. So not only did we algebraically derive the inverses of two different functions, or of a function, of 3 different functions, in fact, but we were able to prove why they are functions by taking the inverse and substituting it into the given function and vice versa, and showing that everything simplifies to be x. So those are the skills that we're going to be practicing for this lesson that is really kind of a precursor to things we're going to be talking about for exponential functions and logarithmic functions. And from here, we'll be moving on. But again, just to recap, one-to-one functions are functions where the x numbers and the y numbers don't repeat. And in order to find an inverse, swap the x and y, solve for y, and then replace y with the inverse notation. And there we go. So make sure if you have any questions, you have them written down, bring them to me in class or in tutoring, and I look forward to seeing you guys soon. Take care.